Look up at the night sky, and what do you see? Pinpricks of light stars, galaxies, the occasional planet floating in what seems like an endless void. But that emptiness. It's an illusion. The space between stars isn't just a blank canvas. It's a swirling, dynamic ocean of secrets, a place where the universe writes its most cryptic messages in invisible ink. This is the interstellar medium, the ISM, a ghostly expanse of gas, dust, and particles so strange, they defy everything we think we know about the cosmos. And today, we're diving headfirst into its 25 most haunting mysteries. Picture this: a single teaspoon of the interstellar medium might seem empty, but hidden within it are clues to the universe's grandest puzzles. Dark matter tugs at galaxies like an unseen hand. Cosmic rays particles moving faster than a bullet race through space with no clear origin. And then there's the dust, not the kind you wipe off your shelves, but tiny, complex molecules that might hold the blueprint for life itself. The ISM isn't just the backdrop of the universe. It's the stage where the greatest cosmic dramas unfold, where stars are born, where galaxies evolve, and where forces we barely understand shape the very fabric of reality. But here's the thing, we've only scratched the surface. Every discovery pulls back another layer, revealing deeper questions. Why does the ISM glow in ways we can't fully explain? What invisible structures lurk within it, bending light and warping space? And could the answers rewrite physics as we know it? Over the next 25 mysteries, we'll journey through the weird, the wondrous, and the downright unexplainable. This isn't just a tour of the unknown. It's an invitation to stand at the edge of human understanding and peer into the abyss. Are you ready? Because the interstellar medium has been waiting to tell its story, and trust me, you won't believe what it has to say. Here's the thing about the interstellar medium: it's not just floating there passively. Something invisible is pulling the strings, shaping its vast, ghostly structures. That something is dark matter, the universe's most elusive architect. We can't see it, we can't touch it, and yet its gravitational grip is so powerful, it bends the very fabric of space around it. Think of it like a cosmic puppeteer, silently rearranging galaxies and sculpting the ISM into sprawling filaments and voids. But how do we know it's there if it's invisible? The clues are written in light. Take gravitational lensing, for example. When light from distant stars or galaxies passes through regions thick with dark matter, it doesn't travel in a straight line, it warps like a car windshield, distorting the view ahead. Astronomers see these faint bends and twists in starlight, tracing the unseen mass that's doing the bending. Then there are galactic halos, the vast, diffuse clouds of matter that surround galaxies. The math says they should be far heavier than what we can actually observe. Stars and gas alone can't account for the way galaxies rotate or hold together. There's something extra, something dark, providing the missing muscle. For decades, scientists have chased particles that might explain this mystery. The leading candidate, WHIM, weakly interacting massive particles. These hypothetical bits of matter barely interact with normal stuff, slipping through our detectors like ghosts. But here's the twist: after years of hunting, from deep underground labs to space-based observatories, we've come up empty. Not a single confirmed WHIM signal. That's left physicists scratching their heads, wondering if dark matter is even made of particles at all, or if we're missing something fundamental about gravity itself. So why does this matter? Because dark matter isn't just a cosmic bystander. It dictates where gas collects in the ISM, where stars ignite, and even how galaxies collide. Without it, the universe as we know it wouldn't exist. Yet despite its overwhelming influence, it remains a riddle, one that challenges everything from particle physics to cosmology. The interstellar medium holds the fingerprints of this enigma, written in gravity and scattered light. And until we crack the code, the full story of our universe remains just out of reach. Imagine a particle streaking through space with more energy than a major league fastball packed into a single subatomic speck. That's not science fiction. It's a cosmic ray, and some of these particles hit Earth with energies so absurdly high, they leave physicists speechless. Where do they come from? That's one of the interstellar medium's most electrifying mysteries. These aren't just random bits of space debris. They're cosmic bullets fired from cosmic accelerators we've yet to fully understand. Take the infamous "oh my God" particle detected in 1991. This single proton slammed into our atmosphere with the energy of a brick dropped from waist height, except it was smaller than an atom. To put that in perspective, it carried 40 million times the energy of anything we've produced in our most powerful particle colliders. The kicker, we still don't know what natural force in the universe could possibly hurl a particle that fast. Supernova, even their explosive fury falls short. Active galactic nuclei with their supermassive black holes, maybe, but the math gets fuzzy when you account for how far these rays travel through the ISM, losing energy as they collide with gas and dust along the way. And that's the real puzzle. Cosmic rays aren't just racing through empty space, they're navigating a minefield. The interstellar medium is filled with turbulent magnetic fields, clouds of plasma, and obstacles that should slow them down or scatter them beyond recognition. Yet somehow, against all odds, these particles reach us with their extreme energies intact. It's like someone firing a rubber band across a crowded stadium, and it's somehow hitting you with the force of a speeding car. So what's accelerating them? One theory points to shockwaves from dying stars, where chaotic magnetic fields might act like a cosmic slingshot. Another suggests monstrous jets erupting from black holes, twisting space-time into natural particle cannons. There's even speculation about dark matter annihilation, exotic physics we've barely begun to unravel. But here's the twist: every time we trace a high-energy cosmic ray back to its origin, the path seems to lead nowhere, or worse, to multiple possible sources at once, as if the universe itself is blurring the evidence. Why does this matter? Because these particles aren't just space oddities. They're messengers carrying encoded details about the most violent events in the cosmos. They shape the chemistry of the ISM, ionizing gas and sparking reactions that birth new molecules. Some scientists believe they might even play a role in the origins of life, seeding planets with the energy needed to jumpstart probiotic chemistry. But until we crack the code of where they come from, we're missing a vital chapter in the story of our universe, one written in particles moving faster than anything we thought possible. We think we know what the universe is made of: protons, neutrons, electrons, all the ordinary stuff that builds planets, stars, and even us. But here's the cosmic plot twist: about half of that normal matter, the baryons we've spent centuries studying, has gone missing. Poof, vanished, not tucked into black holes or hiding in distant galaxies, but just gone. At least that's what the math says. When astronomers tally up all the visible matter in the cosmos, stars, gas, dust, it's only about half of what theories predict should be there. So where's the rest? The answer might lie in one of the most elusive and ghostly structures in existence, the warm-hot intergalactic medium, or WHIM. Imagine the universe as a vast cosmic web, with galaxies strung along invisible threads like beads on a necklace. Those threads, they're not empty. They're rivers of ionized gas, superheated to millions of degrees, but so diffuse they're nearly transparent. This is the WHIM, a fog of matter so thin, a cubic meter of it might hold just a single atom. That's why it's been almost impossible to detect with traditional telescopes. It doesn't glow like stars or absorb light like cold dust. Instead, it whispers its presence through subtle distortions in the light of distant quasars, like a fingerprint smudged on glass. The hunt for these missing baryons has pushed technology to its limits. X-ray telescopes like Chandra and XMM Newton have caught fleeting glimpses, tiny spikes in radiation where the WHIM searing gas brushes against even hotter galaxy clusters. Ultraviolet observatories have spotted the faint absorption lines of oxygen atoms, ionized 5 times over, threaded through the voids between galaxies. Even the cosmic microwave background, the afterglow of the Big Bang, carries faint imprints of where this matter might be hiding. Yet piecing it all together is like trying to map a city using only the reflections in raindrops. Why does this matter? Because the WHIM isn't just lost matter, it's the universe's hidden skeleton. These filaments dictate where galaxies form, how they cluster, and even how the cosmic web evolves over billions of years. Without them, our models of structure in the universe crumble, but the real kicker, even if we account for the WHIM, the numbers still don't quite add up. Some of those baryons are still out there, lurking in forms or places we haven't even imagined yet. Solving this mystery isn't just about finding missing pieces, it's about rewriting our understanding of how the cosmos stitches itself together. And that's the beauty of the interstellar medium. It doesn't just hold stars and gas, it cradles the universe's deepest secrets, waiting for us to look closer, think harder, and maybe, just maybe, catch a glimpse of the invisible threads weaving it all together. The Fermi Paradox asks a haunting question. If the universe is so vast and ancient, where is everybody? With billions of galaxies, trillions of stars, and countless planets that could harbor life, the silence is deafening. But what if the answer isn't about intelligence or ambition? What if the interstellar medium itself is the universe's silent gatekeeper, a cosmic filter so harsh, it scrubs the galaxy clean of civilizations before they ever get the chance to reach out? Take interstellar dust, those tiny, jagged particles drifting between stars. To us, they're a nuisance, scattering light and muddying telescope views. But to a fledgling spacefaring civilization, they could be an insurmountable barrier. Imagine self-replicating probes, the kind we theorize could explore the galaxy exponentially, hitting walls of dust like cars plowing into sand dunes. At high speeds, even microscopic grains become deadly shrapnel, eroding hulls, frying electronics, and grinding ambitions to a halt. The ISM isn't empty, it's a minefield, and each dust speck could be a bullet fired by the cosmos itself. Then there's radiation. Cosmic rays don't just carry mysteries, they carry death. A planet bathed in high-energy particles might see life snuffed out before it ever reaches multicellular complexity. Even if life emerges, frequent radiation bursts could trigger mass extinctions, resetting the evolutionary clock over and over. The ISM isn't just space, it's a gauntlet, and Earth might be one of the rare worlds sheltered enough by its star's magnetic bubble to survive long enough for intelligence to arise. But here's the twist, the filter might not just be physical, it could be temporal. The ISM isn't static. Galaxies go through phases, epochs of calm, punctuated by violent bursts of star formation, black hole eruptions, and gamma-ray surges. A civilization rising during the wrong cosmic era might find itself in a galaxy suddenly flooded with lethal radiation, its window of opportunity slamming shut. We might not hear from aliens because, statistically, most are born too early or too late, their signals lost to the interstellar winds of time. So are we alone? Or are we just survivors blinking into existence during a rare lull in the storm? The ISM doesn't answer, it only whispers its dust and rays the unreadable handwriting of a universe indifferent to the question. But one thing's clear, if the great filter is real, it's not just out there, it's in the void between the stars waiting. One moment, space is silent. The next, an explosion of radio waves brighter than entire galaxies erupts across the cosmos, then vanishes, all in less time than it takes to blink. These are fast radio bursts, or FRB, and they're one of the most baffling phenomena in the universe. Imagine a flash so powerful it outshines 500 million suns, yet lasts just 1,000th of a second. If that wasn't strange enough, some of these bursts don't just fire once, they repeat, flickering on and off like a cosmic lighthouse with no clear rhythm. So where do they come from? The leading suspect, magnetars, the universe's ultimate cosmic tantrum throwers. These are neutron stars with magnetic fields so intense they could strip the data off a credit card from halfway across the galaxy. When a magnet's crust snaps under the strain, it might unleash a burst of energy so violent it ripples through the interstellar medium like a shockwave. But here's the catch: not all FRBs match this explanation. Some arrive from regions of space where no magnet has ever been spotted, and others carry patterns so precise they almost look engineered. That's where the ISM steps in, not just as a backdrop, but as an active player in the mystery. As these radio waves race through space, they pass through clouds of charged particles plasma that twist and delay their signals like glass bending light. By studying these distortions, scientists can map the invisible structure of the interstellar medium itself, almost like using FRBs as cosmic sonar. But sometimes the distortions don't make sense. Certain bursts arrive with far more scattering than the ISM in their path should cause, hinting at dense, unseen pockets of matter hiding between the stars. Could alien civilizations be behind some of these signals? It's unlikely, but not impossible. The repeating patterns have sparked wild theories. Perhaps an advanced species is propelling starships with focused beams of energy, and we're catching the leakage. Or maybe these are interstellar beacons meant to announce their presence. The truth, we don't know. What we do know is that every new FRB detected scrambles our theories a little more, proving the interstellar medium isn't just empty space. It's a dynamic, chaotic frontier where forces we barely understand can whip up bursts of energy so fierce they rewrite the rules of physics on the fly. And that's the thing about FRBs: they're more than just flashes in the dark. They're probes illuminating the darkest corners of the cosmos, revealing structures and phenomena we'd never see otherwise. Each one is a puzzle wrapped in an enigma, hurled across the void to remind us just how much we have left to learn. Deep inside the interstellar medium, where starlight dares not reach, there are places so dense and cold they defy the laws of physics as we know them. These are dark molecular clouds, cosmic nurseries that should, by all accounts, be collapsing under their own weight to birth new stars, but many don't. Some linger for millions of years like statues in the void, resisting gravity's relentless pull. Why? The answer lies in forces so subtle they're almost invisible, yet powerful enough to hold back the inevitable. Take the Taurus molecular cloud, for example. Just 450 light-years away, it's a sprawling maze of gas and dust with pockets so thick not even the Hubble Space Telescope can peer through. Inside, temperatures hover just a few degrees above absolute zero, and pressures should be crushing atoms together into the first sparks of stars, yet vast regions remain eerily still. The culprit: magnetic fields. Threaded through these clouds like invisible spiderwebs, these fields exert a force that counters gravity, propping up the gas like pillars in a cosmic cathedral. Here's where things get weird. According to the Loder-Wilkin law, a decades-old rule linking a cloud's mass to its star-forming potential, these regions should have collapsed long ago. But observations reveal a glaring mismatch. Some clouds with enough mass to form 100 stars barely produce a handful. Others fragment into chaotic swirls, spawning stars at random instead of following neat, predictable patterns. It's as if the universe tossed out the instruction manual and decided to improvise. The secret might lie in turbulence. Imagine stirring a cup of coffee. The whirls and eddies create pockets of chaos that resist smooth motion. Now scale that up to interstellar proportions. Within these clouds, supersonic winds and shockwaves from long-dead stars churn the gas into a froth, preventing it from settling into the orderly collapse needed for star birth. Add magnetic fields into the mix, and you've got a cosmic tug-of-war where gravity doesn't always win. But the biggest twist: some of these stubborn clouds might be hiding a dark matter component, subtly altering their dynamics in ways we can't yet measure. Or perhaps there's exotic chemistry at play, with complex molecules absorbing energy that would otherwise fuel collapse. Every new telescope trained on these enigmatic regions, from ALMA radio eyes to JWST infrared gaze, uncovers more questions than answers. What's clear is this: dark molecular clouds aren't just passive star factories. They're battlefields where unseen forces clash in slow motion, shaping the fate of galaxies one stubborn dust grain at a time. And until we crack their code, the full story of how stars and life emerge from the void will remain tantalizingly out of reach. Starlight carries fingerprints, unique patterns etched into its glow as it journeys through the cosmos. But some of these cosmic signatures have resisted explanation for over a century. Meet the diffuse interstellar bands, or DIB, mysterious dark lines in the spectra of distant stars where something in the interstellar medium has stolen a sliver of light. Discovered way back in 1922, they've baffled generations of astrophysicists. Here's the kicker: despite decades of lab experiments and observations, we still can't pin down exactly what's causing them. The puzzle starts with their sheer stubbornness. Unlike typical absorption lines tied to known atoms or simple molecules, DIBs show up as broad, fuzzy bands, over 500 of them stretching from ultraviolet to infrared. They're not tied to any single element on the periodic table. Carbon chains like those found in comets, polycyclic aromatic hydrocarbons, the soot-like molecules drifting between stars. Early hopes that these might explain the bands crumbled when lab tests failed to produce matching spectra. Whatever's out there absorbing starlight is far more complex than anything we've synthesized on Earth. That complexity hints at something extraordinary. The leading theory suggests massive organic molecules, sprawling structures with dozens or even hundreds of atoms might be the culprits. Picture cages of carbon laced with nitrogen or oxygen, floating in the void, each one a cosmic Rorschach test, absorbing light in ways too intricate for our labs to mimic. But here's the twist: these molecules, if they exist, shouldn't survive long in the harsh interstellar medium. Radiation should shred them, turbulent gas clouds should tear them apart. Yet the DIBs persist, hauntingly consistent across galaxies, as if the universe is taunting us with a chemistry set we can't decode. Even stranger, the bands vary in strength depending on which direction you look. Some regions of space show stronger absorption than others, hinting that these mystery molecules aren't spread evenly but clustered in pockets, like invisible reefs in an interstellar ocean. And while most absorption features shift slightly as light passes through moving gas clouds, certain DIBs stay locked in place, defying the Doppler effect. It's as if whatever's absorbing the light isn't just floating passively, but is somehow anchored to the fabric of space itself. So why does this matter? Because DIBs might hold clues to the universe's hidden chemistry, the very building blocks that could seed planets with probiotic materials. If these bands trace vast reservoirs of complex organics drifting between stars, they could rewrite our understanding of how life's ingredients spread across the cosmos. But until we crack their code, they remain spectral ghosts, whispering secrets we're desperate to hear but can't yet understand. Every new telescope, every advanced spectrometer brings us closer, but for now, the diffuse interstellar bands stand as one of the most enduring riddles written in starlight. Space isn't just a void, it's a cosmic chemistry lab where molecules form under conditions so extreme they'd make any Earth-bound scientist double-check their textbooks. Out in the frigid darkness of the interstellar medium, where temperatures plunge hundreds of degrees below zero and the pressure is virtually non-existent, you'd expect chemistry to grind to a halt. But the opposite happens. Here, in the absence of the heat and pressure we consider essential for reactions, nature gets creative, crafting complex organic molecules like alcohol, sugar, and even amino acids, the very building blocks of life. Take ethanol, for example. Yes, the same alcohol found in your favorite drink has been detected floating in vast clouds near the center of our galaxy. Not just traces enough to fill oceans. Then there's glycolaldehyde, a simple sugar, lurking in star-forming regions light years away. These aren't flukes. Over 200 different molecules have been identified in the ISM, from formaldehyde to acetic acid, each defying the textbook rules of how chemistry should work. So how does it happen? The answer lies on the surfaces of the universe's tiniest architects, interstellar dust grains. Picture a speck of dust smaller than a virus drifting through the void. To us, it's nothing, but in the microscopic world, it's a bustling metropolis. Atoms and molecules, too sparse to react in open space, latch onto these grains where they're forced into close quarters. The dust's cold surface acts like a cosmic dance floor, slowing molecules down just enough for them to bond in ways that would be impossible in the chaos of Earth's warm, crowded environments. Hydrogen meets carbon monoxide, oxygen bumps into methane, and suddenly, complex organics emerge, forged in the frigid stillness of deep space. But here's the twist: some of these reactions shouldn't happen at all. Without the energy of heat or light, certain bonds can't form, at least not according to conventional chemistry. That's where quantum tunneling comes in. On these dust grains, particles don't just collide, they cheat. Thanks to quantum mechanics, atoms can tunnel through energy barriers that would normally block a reaction, vanishing on one side of an obstacle and reappearing on the other, like a ghost walking through walls. This spooky phenomenon lets molecules form in conditions that would leave Earth-bound chemists scratching their heads, and the surprises don't stop there. Some of these space-borne molecules are chiral, meaning they come in mirror image versions like left and right hands. On Earth, life overwhelmingly uses one version, left-handed amino acids, for instance. But in the ISM, both forms exist. That raises a tantalizing question. Did the seeds of life's molecular preference originate in the cold clouds of space long before planets formed? Every new discovery in interstellar chemistry peels back another layer of the universe's hidden ingenuity. The ISM isn't just a passive reservoir of raw materials. It's an active, dynamic kitchen, cooking up the ingredients for stars, planets, and perhaps even life itself. And with each molecule we identify, we're reminded the rules of chemistry aren't universal. Out there, in the silent dark, nature writes its own. In the vast tapestry of the interstellar medium, few sights are more breathtaking or puzzling than HI regions. These colossal bubbles of ionized hydrogen glow like neon signs in the cosmos, lit by the fierce ultraviolet radiation of newborn stars. But look closer and something doesn't add up. These regions don't just sit quietly in space. They seethe and churn, expanding in fits and starts, defying the neat, spherical shapes predicted by simple physics. The reason supernova's stellar explosions so violent, they inject chaos into these delicate structures like a hammer smashing through glass. Take the Orion Nebula, one of the most studied HII regions in our galaxy. At its heart, the trapezium cluster blasts the surrounding gas with enough energy to ionize atoms for light years in every direction. Yet instead of expanding smoothly, the nebula's edges writhe with filaments and tendrils, twisted by shockwaves from long-dead stars. Even more confusing, some parts of the nebula are racing outward at breakneck speeds, while others seem frozen in place. This isn't just random turbulence. It's a cosmic feedback loop where dying stars reshape the very nurseries that birthed them. Here's where things get counterintuitive. The interstellar medium is a low-density environment, so sparse you'd think energy from supernovas would dissipate harmlessly into the void. But the opposite happens. Instead of fading quietly, these shockwaves ricochet off denser gas pockets, creating ripples that can persist for millennia. Imagine tossing a pebble into a pond, only for the ripples to bounce off invisible walls and collide in midair. That's the kind of chaos we're dealing with. The real mystery lies in the math. Simulations suggest supernova energy should quickly dissipate, leaving HI regions to expand calmly. Yet observations reveal violent, uneven motions that refuse to follow the script. One theory points to magnetic fields threading through the gas like invisible wires, resisting and redirecting the explosion's fury. Another suggests cosmic rays, those ultra-fast particles we still don't fully understand, might be pumping extra energy into the mix, stirring the gas like a hidden spoon. But perhaps the most tantalizing clue comes from something called thermal instability. In certain pockets of these regions, cooling and heating processes battle to a standstill, creating zones where gas flips between states like a cosmic switch. One moment it's hot and ionized, the next it's cool and neutral. This flickering could explain why some parts of an HII region surge forward while others lag behind, like a car with a sputtering engine lurching unpredictably down the road. What makes this puzzle so crucial? Because HII regions aren't just pretty cosmic light shows. They're the engines of galactic evolution, sculpting the interstellar medium into new shapes, triggering fresh rounds of star formation, and even determining the fate of entire galaxies. If we can't explain their chaotic dance, we're missing a key chapter in the story of how the universe builds itself. And until we crack the code, these glowing enigmas will keep us guessing, one turbulent bubble at a time. The Milky Way isn't just a scattered collection of stars. It's woven together by an intricate, invisible latticework of filaments, stretching hundreds of light years like cosmic spider silk. These structures, often called the bones of our galaxy, are more than just pretty patterns. They're the scaffolding of star formation, the hidden highways where gas and dust converge under gravity's pull. But here's what's truly wild: we still don't know what sculpts them. Dark matter's gravitational claws, or the interstellar medium's own magnetic fields twisting space into knots. The answer could rewrite how we understand the birth of stars and the architecture of the universe itself. Picture the Nessie filament, a serpentine tendril of gas slithering through the Milky Way's spiral arms. At over 300 light-years long and just 1 light-year wide, it's impossibly slender for something so massive, like a pencil balanced on its tip for millions of years. How does it stay intact? One clue comes from its spine, a string of newborn stars glowing like beads on a string. These stars didn't form randomly. They emerged where denser knots of gas trapped in the filament's grip finally collapsed. But what created those knots? Simulations suggest dark matter's unseen hand might be clumping the gas, while magnetic fields act like cosmic rains, preventing it from dispersing into chaos. Yet not all filaments play by the same rules. Some, like the Musca cloud, bristle with magnetic forces so strong they align dust grains like compass needles, polarizing starlight in eerie, predictable patterns. Others, like the Taurus molecular cloud's filaments, show almost no magnetic signature at all, as if gravity works alone there. This inconsistency is maddening and thrilling. It implies the interstellar medium isn't just a passive canvas but an active sculptor, choosing different tools in different corners of the galaxy, the real mystery. Filaments might be the universe's preferred delivery system for star-making material. In the densest webs, gas flows along these threads like water down a gutter, funneling toward star-forming hubs at staggering speeds. Some calculations suggest up to 80% of a star's mass could arrive via these cosmic pipelines. That would mean filaments aren't just bystanders to star birth, they're the midwives directing the show. But the biggest enigma remains their origins. Are we seeing echoes of the cosmic web, the vast dark matter structure that underpins the entire universe? Or are these threads spun locally by supernova shockwaves and stellar winds? Every new radio telescope mapping their cold, faint glow brings us closer to an answer and deeper into the maze. Because if one thing's clear, it's this: the galaxy's skeleton holds secrets we've only begun to trace. The interstellar medium doesn't just drift aimlessly, it's threaded with invisible forces that twist and shape it like hands molding clay. These are magnetic fields, and while we can't see them directly, their fingerprints are everywhere. gas clouds stretch into eerie filaments, dust grains align like compass needles, and star-forming regions ripple with energy, all because of magnetism's hidden grip. But here's the catch: measuring these fields is like trying to map a hurricane using only the rustle of leaves. The tools we have are ingenious, but they're also frustratingly limited, leaving us with a puzzle that defies easy answers. Take polarized light, our primary window into this invisible realm. When starlight passes through the ISM, dust grains shaped like tiny needles spun by magnetic fields scatter the light in a specific direction, leaving a telltale pattern. It's as if the universe is sending us a coded message, written in the alignment of particles we can't even see. But this method has blind spots. It only reveals the orientation of fields, not their strength, and in dense clouds where stars are born, dust becomes so thick it obscures the signal entirely. That's where the Zeeman effect comes in, a subtle splitting of spectral lines caused by magnetism's tug on atoms. In theory, it's the gold standard for measuring field strength. In practice, it's maddeningly faint. Detecting Zeeman splitting is like listening for a whisper in a thunderstorm. Only the strongest fields, those around nascent stars or within turbulent nebulae, register clearly. Elsewhere, the signal drowns in noise, leaving vast swaths of the ISM uncharted, and the fields we can measure, they're all over the place. Near supernova remnants, magnetism runs wild, with strengths varying by factors of 100 over distances smaller than our solar system. In quiet molecular clouds, fields may be 10,000 times weaker, yet still strong enough to resist gravity's pull and delay star formation. Even more perplexing, some regions show fields twisted into spirals, while others stretch in unnervingly straight lines, as if space itself has preferences we don't yet understand. The real mystery isn't just how these fields behave, it's where they come from. Are they primordial, woven into the universe during the Big Bang, or are they dynamos amplified over eons by the churning of ionized gas? Observations of young galaxies hint at surprisingly strong fields even in the early cosmos, suggesting magnetism might be as fundamental as gravity or light. But without better tools, we're left piecing together fragments, like trying to reconstruct a symphony from a handful of stray notes. What's clear is this: magnetic fields are the silent architects of the interstellar medium, shaping everything from the birth of stars to the trails of cosmic rays. And until we crack their code, we're missing a fundamental language in the universe's grand design, one written not in stars or dust, but in the invisible lines of force that stitch the cosmos together. Dust in space isn't just tiny rocks. It's a gallery of cosmic oddities, each grain a relic of events so violent they defy earthly logic. Among these, nanodiamonds stand out as one of the universe's most perplexing contradictions. These microscopic gems, scattered across the interstellar medium, carry the crystal structure of Earth's diamonds, but they formed without the crushing pressures deep inside a planet. So how does a diamond bloom in the void? The answer might lie in the chaotic aftermath of a supernova's last gasp. When a massive star explodes, it doesn't just vanish in a blaze of light. It hurls its guts across space at speeds approaching 10,000 kilometers per second, creating shockwaves so intense they forge entirely new materials in their wake. Inside these expanding fireballs, carbon atoms torn from the star's core collide and lock into rigid lattices, crystallizing instantly. No billion-year squeeze under continental crusts, no gradual buildup of heat and pressure. Just a single, catastrophic moment that condenses stardust into something harder than steel. But here's the twist: not all nanodiamonds fit this story. Some predate our solar system entirely, their isotopic signatures tracing back to different stars altogether. These presolar nanodiamonds are time capsules, older than the Sun itself, carrying elements like xenon in ratios so bizarre they hint at environments we've never directly observed. Even stranger, a fraction of them contain hydrogen isotopes, suggesting they formed not in supernovas, but in the chilly outskirts of red giant stars, places where diamonds shouldn't be able to grow at all. Then there are the silicate needles, elongated crystals that shouldn't exist under normal interstellar conditions. On Earth, such structures require slow, precise cooling. In space, they're born from chaos, supernova shockwaves, or the violent collisions of asteroid belts. Some even show traces of radioactive aluminum, a smoking gun linking them to the deaths of massive stars. Yet when scientists try to replicate these grains in labs, mimicking the presumed conditions, the results never quite match. The interstellar medium, it seems, has recipes we haven't cracked. What makes these dust grains so fascinating isn't just their origins, it's their resilience. Nanodiamonds forged in stellar explosions should be rare. Instead, they're everywhere. Meteorites haul them to Earth by the trillions. Distant galaxies glitter with their infrared signatures. They've even been detected floating in the atmospheres of white dwarfs, the corpses of stars that might have birthed them. This ubiquity suggests a hidden efficiency in the universe's dust factories, a process we're only beginning to glimpse, and that's the real mystery. If exotic grains like these form so readily, why don't our models predict them? Why do lab experiments fall short? The interstellar medium isn't just a junkyard of cosmic debris, it's an alchemist's workshop, turning chaos into crystals under rules we're still deciphering. Every nanodiamond, every silicate needle is a clue, and until we understand them, a piece of the universe's story remains locked in these tiny, indestructible vaults. Picture a quasar, a beacon of light so blinding it outshines entire galaxies, sending its radiation across billions of light years. By the time that light reaches us, it doesn't arrive pristine. Etched into its spectrum are hundreds, sometimes thousands, of dark absorption lines like scratches on a lens. This is the Lyman alpha forest, and it's one of the most revealing and frustrating clues we have about the structure of the interstellar medium. Each of those lines is a fingerprint marking where the quasar's light has been absorbed by neutral hydrogen clouds along its path. But here's the catch. While these lines expose the ISM's clumpy nature, they refuse to give up their three-dimensional secrets. The phenomenon hinges on a quirk of atomic physics. When ultraviolet light hits a hydrogen atom, it can excite the electron to a higher energy level, specifically the Lyman alpha transition. The absorbed wavelength leaves a dark line in the quasar's spectrum, and the exact position of that line shifts slightly depending on the cloud's velocity relative to us. This means every blob of hydrogen, no matter how distant, stamps its own unique mark on the light. The result, a forest of lines, each representing a different cloud at a different point in space and time. It's as if the universe handed us a cosmic barcode, and we're still learning how to scan it. But why can't we map these clouds in 3D? The problem is perspective. Like trying to decipher a stack of transparent slides pressed together, we see all the absorption lines superimposed. A single line could come from a tiny, dense knot of hydrogen just 1,000 light years away, or a diffuse, sprawling cloud halfway across the universe. Without knowing the exact distance to each absorber, we're left with a dazzling but flat snapshot. Some clever workarounds exist, like cross-referencing multiple quasars to triangulate cloud positions, but the data remains stubbornly ambiguous. The real intrigue lies in what the Lyman alpha forest hints at: the cosmic web. Simulations predict that the universe's matter isn't spread evenly but woven into a vast, sponge-like structure, with galaxies clinging to filaments of dark matter and gas. The forest's absorption lines should, in theory, trace these filaments, yet when we compare observations to models, the match isn't perfect. Some lines appear too broad, suggesting turbulent gas motions we can't explain. Others cluster in ways that defy predictions, as if hidden forces, maybe magnetic fields, maybe something darker, are rearranging the cosmic scaffolding. And then there's the temperature puzzle. The width of Lyman alpha lines betrays the heat of the absorbing gas. Some clouds are frigid, barely a few degrees above absolute zero, while others simmer at tens of thousands of degrees, likely heated by long-ago quasar outbursts or supernova shockwaves. But occasionally, we find lines that don't fit, either extreme, too narrow for hot gas, too broad for cold. These outliers might be signposts of the elusive warm-hot intergalactic medium, the WHIM, that missing reservoir of baryons we've been hunting for decades. The Lyman Alpha Forest is more than a cosmic curiosity. It's a shadow play casting silhouettes of the universe's hidden architecture. Every quasar we observe adds another thread to the tapestry, another clue to how matter swirls and settles in the void. Yet for all its revelations, the forest guards its deepest secrets fiercely, reminding us that even the brightest beacons in the cosmos can't fully illuminate the darkness between the stars. The cosmic microwave background, the faint glow left over from the Big Bang, should be smooth, like a canvas painted with the faintest brushstrokes of temperature variation. But in 2003, astronomers found something that shouldn't be there, a chilling anomaly dubbed the cold spot. This patch of sky, spanning nearly 1 billion light-years, registers significantly colder than its surroundings, as if a cosmic hand had pressed an ice pack against the fabric of space. The question is, what left this ghostly imprint? The answer might lie in the interstellar medium, or in something far stranger. At first glance, the leading theory seems straightforward: a supervoid. These are vast, near-empty regions of the universe where galaxies and matter are conspicuously scarce. If such a void sat between us and the cold spot, the CMB photons passing through it would lose energy due to the universe's expansion, a phenomenon called the integrated Sachs-Wolfe effect. Think of it like rolling a marble up a hill that's gradually flattening. The marble slows as the slope changes. Similarly, photons traversing a void would emerge slightly colder, creating the observed temperature dip. But here's where things get murky. Surveys mapping galaxy distributions in the cold spot's direction reveal underdense regions, just not empty enough to fully explain the temperature drop. The deficit of matter is there, but the math falls short by a staggering margin. Some calculations suggest the void would need to be twice as large or 3 times as empty as what we've observed to account for the anomaly. That leaves 2 possibilities. Either our understanding of voids and the ISM's role in photon cooling is woefully incomplete, or the cold spot isn't a void shadow at all. Enter the wild card parallel universes. In a speculative but mathematically coherent twist, some theorists propose the cold spot could be a bruise left by a collision with another bubble universe during cosmic inflation. The idea hinges on multiverse models where our universe is one of many, each with its own physical constants, bubbling up from an eternally inflating space-time foam. If one of these bubbles grazed ours in the distant past, the energy release could have imprinted a cold signature on the CMB. It's a radical notion, but not an impossible one, especially when conventional explanations keep coming up short. The interstellar medium complicates the picture further. Even if a supervoid is partially responsible, the ISM's turbulent, magnetized layers could be distorting the signal. Dust and plasma might scatter or absorb photons in ways we haven't accounted for, muddying the temperature readings. Meanwhile, polarized light studies hint at unusual magnetic field alignments near the cold spot, as if some unseen force has combed the ISM into unnatural order. For now, the cold spot remains one of cosmology's most tantalizing riddles. It challenges not just our models of voids and the ISM, but the very limits of what we consider plausible. Whether it's a cosmic trick of the light, a flaw in our theories, or evidence of realities beyond our own, one thing is certain: the universe is still full of surprises, and the interstellar medium is keeping its secrets well. In the grand accounting of the universe, helium-3 is missing. Not just a little bit, entire galaxies worth. This lightweight isotope of helium, produced copiously during the Big Bang, should be floating through the interstellar medium in quantities that match our earliest cosmic blueprints. But when astronomers tally it up today, the numbers don't just fall short, they're off by staggering margins. So where did all that helium-3 go? The answer might rewrite our understanding of how stars live, die, and even how planets hoard their secrets. Start with the basics. Helium-3 is helium's shy cousin with 2 protons but just 1 neutron. Born in the universe's first minutes, it's been drifting through space for over 13 billion years. Theory says it should be everywhere, especially in the diffuse clouds between stars. Yet when we measure its abundance, it's barely a third of what early universe models predict. The discrepancy is too large to ignore. Either our models are fundamentally flawed, or something out there is systematically destroying or hiding this isotope on a cosmic scale. Stars are prime suspects. Inside their cores, hydrogen fuses into helium-3 before converting further into ordinary helium-4. Conventional wisdom held that this helium-3 gets burned up entirely, but recent studies reveal a shocking inefficiency. Up to 80% of a star's helium-3 might survive its lifetime, expelled into space via stellar winds or supernova. If that's true, the ISM should be swimming in the stuff. Yet it's not. This leaves us with 2 possibilities. Either stars are somehow destroying helium-3 after producing it, or something else is intercepting it before we can see it. Enter gas giants, specifically the helium rain hypothesis. Deep inside planets like Jupiter and Saturn, where pressures reach millions of times Earth's atmosphere, helium might be separating from hydrogen and forming droplets that fall like rain toward the core. This process could preferentially sequester helium-3, dragging it out of circulation. Laboratory experiments using diamond anvils to simulate these extreme conditions show that helium-3 behaves differently than its heavier counterpart, possibly sinking faster under certain pressures. If this happens across countless gas giants throughout the galaxy, it could explain the isotope's mysterious disappearance, but there's a catch. Even if every gas giant in the Milky Way hoarded helium-3 like cosmic misers, the math still doesn't quite balance. Which raises an even wilder idea. What if the missing helium-3 is hiding in plain sight, trapped in a form we've overlooked? Some theorists propose it could be bound up in complex molecules or icy dust grains, invisible to our current detection methods. Others wonder if supernova shockwaves are breaking it apart entirely, transforming it into other elements. The vanishing helium-3 problem isn't just a bookkeeping error. It's a clue, one that challenges our assumptions about nucleosynthesis, stellar evolution, and even planetary interiors. Solving it might require rewriting the recipes of stars and rethinking the hidden chemistry of gas giants. Until then, the universe's ledger remains unbalanced, with a line item that stubbornly refuses to add up. Space isn't just cold, it's inhumanely cold, with temperatures plunging close to absolute zero in the darkest voids between stars. So when NASA's Chandra X-ray Observatory peered into these regions and found pockets of gas blazing at millions of degrees, scientists were left staring at their screens in disbelief. This wasn't just a curiosity, it was a full-blown thermodynamic rebellion, a cosmic defiance of everything we thought we knew about heat and emptiness. How could the interstellar medium, a place where molecules struggle to muster enough energy to twitch, suddenly turn into a furnace? The answer, or lack thereof, has sent astrophysicists back to the drawing board, questioning some of their most trusted models. Take supernovas, the universe's ultimate pressure cookers. When a massive star explodes, it unleashes shockwaves that rip through the ISM at tens of thousands of kilometers per second. For decades, these shockwaves were the go-to explanation for hot gas pockets. The math seemed solid: slam enough energy into diffuse hydrogen and it should heat up. But Chandra's data revealed a glaring mismatch. The hottest gas clusters weren't neatly lining up with supernova remnants. Some floated in regions eerily quiet, far from any recent stellar cataclysms. Even stranger, the temperature profiles didn't decay as predicted. Instead of gradually cooling, these zones simmered at extreme heats for way longer than any shockwave model could justify. It's like tossing a lit match into a snowbank and finding it still burning a week later. That's where turbulence comes in, or more accurately, where it complicates everything. The interstellar medium isn't a placid pool, it's a maelstrom of magnetized chaos. Gas swirls, collides, and twists in fractal patterns, creating eddies within eddies. Under the right conditions, this churning could act like a cosmic microwave, converting motion into heat through a process called viscous dissipation. Picture stirring a cup of coffee with a spoon. The tiny vortices near the spoon's edge generate friction, warming the liquid ever so slightly. Now scale that up to interstellar proportions, with magnetic fields acting as invisible spoons stirring gas across light years. Theoretically, this could explain some of the heating, but the numbers still don't add up. Even the most generous turbulence models fall short of the observed temperatures by at least an order of magnitude. Then there's the dark horse candidate, cosmic rays. These high-energy particles, zipping through space at near-light speeds, might be dumping their energy into the ISM like microscopic arsonists. When a cosmic ray collides with a hydrogen atom, it can transfer enough kinetic energy to ionize the gas, heating it up in the process. The problem: cosmic rays are notoriously slippery. They don't just stop and deposit all their energy in one place. They ricochet, deflect, and often escape into intergalactic space before doing much heating. Unless there's some yet undiscovered mechanism trapping them in specific regions, they can't fully account for the localized infernos Chandra has spotted. The most tantalizing clue might lie in something called magnetic reconnection, a process where tangled magnetic field lines suddenly snap and reconfigure, releasing bursts of energy. We see this on the Sun, where it triggers solar flares hotter than the core of a nuclear blast. If similar events occur in the ISM, they could explain the sporadic, intense heating. But interstellar magnetic fields are orders of magnitude weaker than the Sun's, making it unclear whether reconnection could pack enough punch. Unless, of course, we're missing a key variable, like hidden currents of dark matter or exotic plasma physics we haven't yet modeled. What's clear is this: the million-degree gas pockets aren't just anomalies. They're signposts pointing to gaps in our understanding of energy transfer in space. Every time we think we've nailed down the mechanism, the interstellar medium laughs and reveals another layer of complexity. And until we crack this paradox, we're left with a universe that refuses to play by the rules, one where the coldest voids can suddenly, inexplicably catch fire. Deep in the frigid heart of interstellar clouds, where temperatures hover just a whisper above absolute zero, something impossible is happening. The Atacama Large Millimeter Array ALMA has been picking up strange, rhythmic emissions from these cosmic freezers, signals pulsing with a regularity that defies conventional physics. These aren't the chaotic bursts of star formation or the predictable hum of carbon monoxide snowlines, where gas freezes into frost like a cosmic winter. No, these waves are different. They're precise, almost musical, as if the universe has hidden a metronome inside its coldest vaults. Take the case of the Taurus molecular cloud, a starless void where ALMA detected millimeter wave flickering in perfect, repeating intervals. At first, scientists assumed it was just spinning dust, tiny grains tumbling through magnetic fields, emitting radiation like microscopic lighthouses. But the math didn't add up. For dust to produce such clean, steady signals, the grains would need to rotate at impossible speeds, faster than any known force in the ISM could propel them. Even stranger, the emission patterns didn't match any known molecular transition. It was as if the cloud itself was humming a tune written in a language we've never heard. Then there's the contrast with CO snowlines, regions so cold, carbon monoxide freezes onto dust grains like frost on a window pane. These zones are textbook predictable. Their chemistry follows rigid rules, their boundaries sharp as a knife's edge. But these unexplained emissions, they laugh at textbooks. They flicker in clouds devoid of the complex molecules normally linked to such signals, and they cluster in patches too small and fleeting to map. Some researchers wonder if they're catching quantum effects in real time, nano-dust grains exhibiting bizarre properties when chilled to near absolute zero. Others whisper about entirely new physics, like action-like particles converting dark matter's ghostly presence into detectable waves. The most tantalizing clue might lie in the signal's timing. Unlike cosmic noise, which sputters randomly, these pulses keep cadence like a drumbeat felt across light years. Could it be some natural resonator, a structure in the ISM vibrating under unseen forces? Or more radically, might we be seeing the fingerprints of a process that rewrites how energy moves through space? Every new observation deepens the mystery, proving that even in the coldest, quietest corners of the universe, the interstellar medium still has stories to tell. And if we learn to listen, we might just hear the future of physics itself. Dark energy isn't just stretching the cosmos on grand scales. It might be pulling at the interstellar medium's very fabric, warping the void between stars in ways we're only beginning to glimpse. The Hubble tension, the growing discrepancy between how fast we measure the universe expanding locally versus predictions from the early cosmos, hints that something's off in our equations. Could dark energy be flexing its influence unevenly, tugging harder at the ISM's emptiest regions than we ever anticipated? Picture a cosmic game of tug-of-war. On one side, gravity tries to clump matter into galaxies and filaments. On the other, dark energy pushes space itself apart, accelerating the expansion. In dense regions like galactic clusters, gravity holds its ground, but in the vast voids between them where the ISM thins to near nothingness, dark energy might gain the upper hand. Some observations suggest these voids are expanding faster than standard models predict, as if an invisible hand is propping them open. The Planck satellite's measurements of the cosmic microwave background initially pegged the universe's expansion rate at 67 kilometers per second per megaparsec. Yet local measurements of supernova and Cepheid variables consistently land near 73. That gap, the Hubble tension, might be a clue that dark energy's grip varies with the environment, like a tide that's stronger in some coves than others. Here's where the interstellar medium becomes a critical testing ground. If dark energy interacts differently with sparse gas clouds versus dense molecular cores, we should see subtle distortions in how these structures evolve. For instance, the Smith cloud, a massive, high-velocity hydrogen streamer hurtling toward the Milky Way, shows peculiar kinematics that don't quite match pure gravitational models. Could an extra nudge from dark energy's local push explain its trajectory? Or consider the local void, a cavernous emptiness bordering our galaxy where stars are conspicuously absent. Surveys reveal its edges are receding faster than expected, as if space itself is stretching thinner there, like dough pulled too hard at the seams, the wildest possibility. Dark energy isn't a constant force but a dynamic one, ebbing and flowing with the universe's structure. Some theories propose it clusters subtly around cosmic voids, amplifying their expansion like a feedback loop. Others suggest it couples with dark matter in ways that leave faint imprints on the ISM's distribution. If true, this would mean the interstellar medium isn't just a passive backdrop but an active participant in the universe's accelerating fate, its sparse pockets serving as dark energy's testing grounds. Yet for all these tantalizing hints, the evidence remains frustratingly indirect. Mapping dark energy's local effects is like trying to track a ghost by the ripples in its cloak. Current telescopes lack the precision to measure tiny variations in the ISM's expansion, and simulations struggle to reconcile galaxy-scale observations with universe-wide trends. Upcoming missions like Euclid and the Vera Rubin Observatory aim to close this gap, hunting for distortions in the cosmic web that might betray dark energy's fingerprints. Until then, the interstellar medium keeps its secrets, stretching silently between the stars, a cosmic canvas where the universe's most enigmatic force might be quietly rewriting the rules. The ghostly filaments known as infrared cirrus drift through the interstellar medium like cosmic cobwebs, ethereal, glowing structures that shouldn't exist. Seen through infrared telescopes, these wispy tendrils stretch across hundreds of light years, radiating heat without any obvious source. No stars ignite within them. No stellar nurseries pulse at their cores. Instead, they glow with a pale, uniform light, as if the dust itself were whispering secrets from the dark. So why do they shine? One leading theory points to starlight fossils, photons from ancient stars, long since dead, still bouncing between dust grains like echoes in a canyon. When massive stars end their lives in supernova, their light doesn't just vanish. It lingers, absorbed by surrounding dust and re-emitted as infrared waves over millennia. These cirrus clouds might be the afterglow of stellar deaths that occurred before our solar system even formed, their energy preserved in a cosmic game of hot potato between microscopic particles. But there's a problem with this elegant explanation. Some infrared cirrus clouds float in regions devoid of any known supernova remnants, no pulsars, no shockwaves, no telltale shells of expanding gas. Even stranger, their temperatures don't match predictions. If they were truly just warmed by ancient starlight, they should have cooled to near absolute zero by now. Instead, many hover around 15 to 20 degrees above it, as if some unseen hand is gently reheating them. That's where the dust without stars hypothesis comes in. Normally, dust grains need stars nearby to keep them warm. But what if certain particles can generate their own heat? Laboratory experiments suggest some interstellar dust might contain exotic materials like hydrogenated nanodiamonds or metallic whiskers that absorb faint energy from cosmic rays or magnetic fields and release it as infrared glow. It's akin to how a microwave heats food not by external flames but by energizing molecules directly. If these self-warming grains exist, they could explain why cirrus clouds flicker in the darkest voids far from any stellar hearth. Yet the most haunting possibility ties these filaments to dark matter. Some theorists speculate that weakly interacting massive particles, WHIM, could collide in the depths of space, annihilating each other and releasing energy that subtly heats nearby dust. While there's no direct evidence yet, the idea is tantalizing. These ghostly clouds might be mapping the invisible scaffolding of the universe itself, their infrared glow tracing the footsteps of matter we can't see. Whatever their origin, infrared cirrus clouds are more than just cosmic curiosities. They're reminders that the interstellar medium isn't just empty space, it's an archive, a canvas, and a laboratory all at once. And until we decode their mysteries, they'll keep glowing softly in the dark, the universe's way of asking, have you figured me out yet? Starlight isn't just light, it's a message carrying hidden clues about the vastness it traverses. One of its most cryptic signatures, polarization, the subtle twisting of light waves as they pass through the interstellar medium. Normally, this twisting is gentle, predictable, a slight alignment caused by dust grains drifting in magnetic fields. But sometimes the universe throws us a curveball. Certain patches of starlight arrive over-polarized, twisted far more than our models say they should be. It's as if the cosmos took a perfectly straight arrow and bent it into a corkscrew mid-flight. So what's warping the light so violently? The answer might rewrite how we see magnetic fields, or the very dust that shapes them. Start with the basics. Interstellar dust grains aren't just random specks. Many are oblong, like microscopic toothpicks, and when they're caught in magnetic fields, they tend to align with their long axes perpendicular to the field lines. As starlight passes through these ordered grains, its electric field vibrates preferentially in one direction, hence polarization. For decades, this process seemed straightforward. Measure the polarization, map the magnetic field, but then came the anomalies. In regions like the Taurus molecular cloud, certain stars' light showed polarization rates up to 20% higher than theoretical maximums. That's like pouring a cup of water into a glass and watching it inexplicably overflow by an extra fifth. One explanation: our magnetic field estimates could be wildly off. If the ISM's fields are stronger or more tangled than we've assumed, they might torque dust grains into tighter alignment, cranking up polarization to extreme levels. There's precedent for this. Some radio observations of galactic nuclei reveal magnetic fields so intense they rival the gravitational pull of supermassive black holes. Could similar, if subtler forces be at work in seemingly quiet molecular clouds? The problem is, direct measurements of these fields are notoriously tricky, leaving us with more questions than answers. Then there's the dust itself. What if the grains aren't just passive aligners but active participants in this twist? Recent lab experiments suggest some interstellar dust might be ferromagnetic, containing tiny flecks of iron or other metals that amplify their response to magnetic fields. Picture a compass needle snapping to attention, except these needles are nanoscale, and their collective alignment could polarize light far more efficiently than plain silicate or carbon grains. Even stranger, certain organic molecules in the ISM might form helical structures, spirals that could mechanically twist passing light like a celestial pasta fork. But the real plot twist comes from where we see these anomalies. Over-polarization clusters oddly, often in regions with intense turbulence or near supernova remnants. That hints at another player: shockwaves. When a star explodes, the blast doesn't just heat gas, it can violently comb magnetic fields into temporary order, like smoothing a crumpled sheet with a sudden yank. If dust grains get caught in this fleeting alignment, they might create localized pockets of extreme polarization before chaos returns. The catch: these spikes should be brief, yet some over-polarized light seems to linger in quiet regions, defying the ephemeral nature of shocks. The consequence: we might be missing a fundamental piece of interstellar physics, one where dust, magnetism, and turbulence interact in ways our models don't yet capture. Every over-twisted photon is a clue, a whisper from the dark urging us to look deeper. Because if we can decode why some light bends too far, we might just unravel how the universe weaves its invisible forces into the fabric of space itself. The universe has a lithium problem, a discrepancy so glaring, it threatens to upend our understanding of the Big Bang itself. According to primordial nucleosynthesis, the explosive aftermath of the cosmos's birth should have forged precise amounts of helium, deuterium, and lithium. And while helium and deuterium match predictions flawlessly, lithium clocks in at a mere third of what it should be. Where did it all go? The answer might not lie in the fiery hearts of stars or the voids between galaxies, but in the interstellar medium's shadowy chemistry, where lithium vanishes like a cosmic magician's trick. Start with the basics. Lithium is fragile. The seventh lightest element, it's easily destroyed in stellar furnaces, where temperatures above 2.5 million Kelvin rip its nucleus apart. This explains why older stars, those formed from nearly pure Big Bang material, show even less lithium than newer ones, but stellar destruction alone can't account for the deficit. Enter the ISM, where lithium's survival hinges on a delicate dance between creation and obliteration. In diffuse clouds, lithium atoms cling to dust grains or bind with other elements, forming molecules like lithium hydride that shield them from destructive ultraviolet radiation. These molecular lifeboats might ferry lithium safely through the galaxy's harsh stretches, except when they don't. Here's the twist: the ISM doesn't just protect lithium, it recycles it. Supernova shockwaves and turbulent gas flows spit lithium back into space, where it's either reincorporated into new stars or broken down further. Observations of young, lithium-rich stars suggest this cycle is real, yet the numbers still don't add up. Somewhere in the churn between stellar death and rebirth, an inexplicable fraction of lithium vanishes. One possibility: the ISM's dust grains are more efficient lithium traps than we've realized. Lab experiments show certain carbonaceous grains can lock away lithium atoms in cage-like structures, effectively burying them for billions of years. But the plot thickens beyond our galaxy. Quasar absorption spectra, the fingerprints of distant gas clouds, reveal that intergalactic lithium levels are even lower than galactic ones. This suggests the ISM isn't the only culprit. Something about the universe's large-scale structure actively suppresses lithium. Could dark matter interactions be transmuting it into other elements? Or are we overlooking a primordial process that stunted lithium's growth in the universe's first minutes? The stakes couldn't be higher. If lithium's absence stems from flaws in Big Bang nucleosynthesis models, it could force us to rethink the very elements that seeded stars, planets, and life itself. For now, the interstellar medium remains both suspect and alibi, a stage where lithium's cosmic drama plays out in whispers and shadows. Every new telescope probing its depths, every lab experiment replicating its conditions brings us closer to the truth. But until then, the universe keeps its lithium ledger unbalanced, a quiet reminder that even the smallest atoms can hold the biggest secrets. When a star dies, we expect fireworks, a blinding supernova flare visible across the universe. But astronomers are catching stars vanishing without a trace, disappearing into the night as if someone flipped a cosmic switch. These silent supernovae challenge everything we thought we knew about stellar deaths, suggesting some stars might skip the explosive finale entirely, imploding straight into black holes like cosmic magic tricks. Take the case of N6942, a red supergiant in the galaxy NGC 6946. In 2008, it shone 25 times brighter than our Sun. By 2015, it was simply gone. No supernova, no fading embers, just an empty patch of sky where a massive star once burned, the leading theory. The star collapsed directly into a black hole, its outer layers falling inward so fast they never rebounded into the expected explosion. It's as if the star tripped over its own gravity, swallowed whole by the very singularity it birthed. But why don't all massive stars go out with a bang? The answer might lie in their cores. Traditional supernovae occur when a star's collapsing core rebounds off its own dense matter, sending shockwaves tearing through the outer layers. But if the core is too massive or rotates too quickly, that rebound might fizzle, like a match failing to light in damp air. The result, a failed supernova where the entire star plunges into oblivion without so much as a cosmic whimper. Simulations suggest this could happen to stars between 20 and 40 solar masses, just heavy enough to doom themselves to silence. Then there's the dust factor. Some supernova might not be silent at all, just smothered. In dense stellar nurseries, clouds of interstellar dust can cloak an explosion entirely, absorbing its visible light and re-emitting it as infrared radiation. The supernova is there, but hidden like a flashlight wrapped in a thick blanket. Infrared surveys have caught hints of these buried explosions, their energy bleeding through the dust as faint heat signatures rather than brilliant flares. It's possible we've missed entire populations of supernovas simply because they're too shy to shine through the cosmic clutter. The implications are staggering. If silent supernovae are common, we may be drastically underestimating how many black holes form in the universe and how quickly. It also complicates our search for gravitational waves, since these stealthy collapses would emit far weaker ripples in spacetime than their explosive counterparts. But the most haunting possibility, some stars might be dying right now, vanishing without a trace, and we wouldn't even know until their light flickers out centuries later. The universe, it seems, still holds some farewells too quiet for us to hear. Space isn't truly empty, not even close. Lurking beneath the apparent stillness of the interstellar medium is a seething quantum foam, where particles flicker in and out of existence so fast they defy the very concept of nothingness. These quantum fluctuations aren't just theoretical curiosities, they exert real, measurable force. It's called the Casimir effect, and if its influence stretches beyond lab experiments into the vastness of space, it could be quietly reshaping the future of interstellar travel. Picture two metal plates placed microscopically close together in a vacuum. According to quantum theory, the space between them should buzz with virtual particles, short-lived pairs of matter and antimatter popping into existence before annihilating each other. But here's the catch: only certain wavelengths of these fluctuations can fit between the plates, while outside, all wavelengths thrive. This imbalance creates a pressure difference, pushing the plates together with a force so precise we've measured it in laboratories. Now imagine that same force acting on a spacecraft coasting through the ISM, where the quantum vacuum isn't constrained by metal plates but by the fabric of space itself. Could these phantom particles subtly drag on ships, sapping their speed over light years? The stakes get higher when you consider the EM drive, a propulsion concept that promised thrust without fuel, violating classical physics conservation of momentum. Early tests showed faint but measurable thrust, sparking both excitement and skepticism. One fringe theory suggested the drive might be interacting with quantum vacuum fluctuations, effectively pushing off the fabric of spacetime itself. Mainstream physics dismissed it as experimental error, but the debate raised a haunting question. If the quantum vacuum can influence objects at microscopic scales, why not macroscopic ones? Even a minuscule drag across interstellar distances could compound into mission-killing delays, but the real puzzle lies in the interstellar medium's density. Quantum fluctuations are everywhere, but their net effect should cancel out in open space unless the ISM's sparse atoms interact with them in unexpected ways. Some models propose that magnetic fields threading through interstellar clouds might polarize the vacuum, creating regions where the Casimir effect's influence fluctuates. A ship passing through these patches could experience unpredictable resistance, like a boat encountering invisible currents. So far, no mission has detected this quantum drag, but no mission has been sensitive enough to rule it out either. As we aim for the stars, this phantom friction remains a specter in the equations, a reminder that even the void between galaxies might not be as passive as it seems. The universe's quietest forces could hold the keys to our fastest journeys if only we learn to listen. Could the interstellar medium be more than just gas and dust? Could it, in some strange way, be alive? Not in the way we think of life on Earth, but as a vast, evolving system that mimics the patterns of biology across cosmic scales. The idea sounds like science fiction, but some of the brightest minds in astrophysics have dared to take it seriously. Take Fred Hoyle, the iconoclastic astronomer who proposed something radical. The ISM might function like a galactic-scale ecosystem, with complex molecules and maybe even microbial life riding its currents like cosmic plankton. Hoyle's panspermia hypothesis suggests life didn't start on Earth at all. It hitchhiked here aboard comets or interstellar dust, seeding our planet like a spore carried by the wind. At first glance, it seems outlandish. Space is unforgiving, a vacuum bathed in radiation where temperatures swing from absolute zero to millions of degrees. But extremophiles, Earth's hardiest microbes, have shattered our assumptions about where life can endure. Some thrive in nuclear reactor cores, others in boiling acid or the crushing depths of the ocean. If life can persist there, why not in the shielded cracks of icy dust grains drifting between stars? The numbers are tantalizing. The ISM is littered with organic molecules, alcohols, sugars, even amino acids floating in clouds dense enough to shield them from the harshest radiation. In labs, scientists have blasted microbes like Deinococcus radiodurans with levels of radiation that would kill a human instantly, only to watch them repair their DNA and keep multiplying. Freeze-dried, these organisms can survive for millennia. Toss them into the void, and they might just sleep until they stumble upon a habitable world. But Hoyle took it further. He imagined the ISM as a dynamic network where molecules evolve through trial and error, not via Darwinian competition but through sheer probability. In his vision, certain molecular configurations like viruses or self-replicating crystals could arise spontaneously in nebular clouds, spreading via stellar winds like a cosmic pandemic. It's a staggering thought. The same forces that birth stars might also spin up precursors to life, scattering them like dandelion seeds across the galaxy. The most provocative evidence: unexplained absorption lines in starlight that match nothing in our chemical libraries. Could these spectral fingerprints belong to complex, carbon-based structures we've never seen, or even something akin to viral particles? We've already found buckaballs, soccer ball-shaped carbon molecules floating in planetary nebulae. If nature is building those, what's stopping it from assembling something even more intricate? Of course, skeptics abound. The leap from complex molecules to life is enormous, and the ISM's low densities make sustained chemical reactions seem unlikely. But consider this: Earth's entire biosphere was once a sterile rock. If life did arrive here from elsewhere, the ISM isn't just a backdrop. It's the delivery truck, the incubator, and maybe even the factory. Every time we discover a new organic molecule in space, the line between chemistry and biology blurs a little more. So is the interstellar medium alive. Not in any way we'd recognize, but if it's cradling the ingredients or even the blueprints for life to emerge elsewhere, then it's something far stranger, a cosmic womb, silent and dark, patiently assembling the pieces of a puzzle we're only beginning to glimpse. The interstellar medium isn't just the space between stars. It's a living, breathing frontier, a cosmic laboratory where the universe's greatest mysteries collide. From the ghostly pull of dark matter to the violent birth of stars, from the whispers of alien chemistry to the fireworks of supernovas that never were, these 25 riddles reveal the ISM as anything but empty. It's a place where particles move faster than thought, where diamonds form in the void, and where the very laws of physics seem to bend under the weight of the unknown. But here's what's truly exhilarating: every mystery we've explored isn't just a curiosity, it's a doorway. Crack the code of dark matter's grip, and we might finally understand the invisible scaffold holding galaxies together. Decipher the origins of cosmic rays, and we could harness energies beyond our wildest dreams. Unravel the secrets of interstellar chemistry, and we might stumble upon the building blocks of life itself, proof that we're not alone in the universe. Even the quirkiest puzzles, like over-polarized starlight or vanishing helium-3, hint at forces and particles we've yet to imagine, lurking just beyond the edge of our equations. This isn't just astronomy, it's detective work on a galactic scale. Every telescope pointed at the night sky, every lab experiment replicating space's harsh conditions, every algorithm sifting through data brings us closer to answers that could rewrite textbooks. And the best part, you don't need a PhD to be part of it. The universe invites everyone to look up and wonder. So tell us, which of these mysteries pulls at your curiosity the most? Is it the enigma of dark matter's shadow, the possibility of life riding cosmic dust, or something else entirely? Drop your thoughts in the comments, and don't forget to step outside tonight. Because the greatest show in the cosmos is happening right above you, in the vast, uncharted wilds of the interstellar medium. The next big discovery could be moments away, and it might just change everything.